Have you ever stopped to think about the invisible forces that are literally powering our entire world? I mean, from the sunlight that warms your face to the Wi-Fi signal that's probably delivering this to you right now, it's all connected by one incredible phenomenon. Let's dive in.
So let's just start with a quick question. What do you think sunlight, your Wi-Fi, and a medical X-ray actually have in common? I know, they seem totally unrelated, right? One you can see and feel, one is totally invisible but connects you to the internet, and the other sees through your skin. But believe it or not, they're all part of the exact same family. And by the end of this, you're going to see exactly how.
To get it, we need to look at what's happening at the most fundamental level. We're talking about this invisible dance, an idea first dreamed up by the brilliant physicist James Clerk Maxwell. He figured out how these waves could even exist, and it all starts with this beautiful self-sustaining loop.
Okay, so what is an electromagnetic wave really? At its heart, it's this disturbance that's made of two parts that are forever linked, an electric field and a magnetic field. Just picture them as two partners in a dance, wiggling or oscillating, in perfect time with each other as they zip through space.
Now, this is where it gets really elegant. How do they keep going? Well, it's this amazing domino effect. You get a changing electric field, and that, in turn, creates a changing magnetic field right next to it. And guess what? That new changing magnetic field then creates a new electric field a little further on. They just leapfrog over and over, constantly creating each other as they fly through space. It's this self-sustaining dance that lets them travel for billions of years across the universe. And this dance, it's got a very specific choreography. The electric field is wiggling up and down, the magnetic field is wiggling side to side, and the wave itself is shooting straight forward. All of them are perfectly perpendicular to each other. You've actually seen this before. If you've ever taken a rope and just flicked your wrist, you see the wave go up and down, but the energy travels forward, away from you. That's a transverse wave, and it's the exact same idea here.
So, we know how they're born, but what are the rules they follow? What really makes these waves, well, what makes them so special?
And this right here is probably their most mind-bending trick. Unlike sound, which needs something to travel through, like air or water, electromagnetic waves need absolutely nothing. They can just cruise through the cold, empty vacuum of space. It's the whole reason we can see the light from stars that are billions of light years away. Their dance doesn't need a dance floor.
All right, so let's just quickly recap the main rules. 1, they're transverse waves, just like that rope we talked about. 2, the energy is split perfectly, 50-50, between the electric and magnetic fields. And 3, and this one sounds a little like science fiction, they can actually push on things. They carry momentum.
That's right. Light actually has a little bit of punch. It's a tiny, tiny amount of force for sure, but because these waves carry momentum, they can exert real physical pressure. And this isn't just a fun theory. It's the core idea behind things like solar sails, these giant reflective sheets designed to sail across the solar system powered by nothing but the gentle, constant push of sunlight. How cool is that?
This brings us to the grand finale. See, we've been talking about EM waves like they're all one thing, but the truth is, they're a massive, diverse family. So it's about time we met the whole clan, the electromagnetic spectrum.
The spectrum is really just a way of organizing all the different types of these waves. Think of it like a big family portrait, with all the relatives lined up, neatly arranged from the lowest energy to the highest. And what defines their spot in line is their wavelength and their frequency.
And here it is, the whole family photo. On one side, you've got radio waves with these really long, lazy wavelengths and low energy. Then, all the way on the other end, you have gamma rays with super short, frantic wavelengths and a ton of energy. And here's the most important thing to get. As the wavelength gets shorter, the frequency and the energy goes way up. It's a perfect inverse relationship. Now let's just quickly say hi to a few of them.
Kicking things off at the low energy end, you've got radio waves. Their wavelengths can be as long as buildings. This lets them travel huge distances without getting blocked, which is, of course, perfect for broadcasting your favorite music all across the country.
Next up, microwaves. They've got shorter wavelengths, and their frequency is just perfect for making water molecules vibrate like crazy, which is exactly how they heat up your leftovers. And that same talent makes them great at carrying all the data for your cell phone and Wi-Fi.
Moving on up the energy ladder, we get to infrared. Now, your eyes can't see it, but you can definitely feel it. It's heat. Anything that's warm, including you, is giving off infrared waves, which is how thermal cameras can see in total darkness.
And then we get to this unbelievably tiny little slice of the whole spectrum. This is visible light. It's the only part that our eyes have evolved to see. Every single color you've ever seen, from red to violet, exists in just this narrow little window.
Right past what we can see is ultraviolet light, or UV. These waves are a bit more energetic, carrying enough of a punch to actually mess with our skin cells. And that's exactly why UV light is responsible for both your summer tan and a really nasty sunburn.
And now, circling all the way back to our first question, we've got X-rays. Their high energy and short wavelengths let them zip right through soft stuff like skin, but get stopped by dense things like bone. And voila! That gives doctors a perfect shadow picture of what's going on inside your body.
And finally, at the top of the charts, the most energetic of all, gamma rays. These are the heavy hitters. They're born from the most extreme events in the cosmos, like stars exploding. They pack so much energy that, thankfully, our atmosphere does a great job of protecting us from them.
So, what's the big takeaway from all this? It's that from the gentle radio wave that brings you music to the intense gamma ray from a distant galaxy, they're all the same thing. They're all just different flavors of light. They're all electromagnetic waves, just dancing to a different beat.
Think about it. We've taken this invisible spectrum and built our entire modern, connected world on top of it. It just makes you wonder, now that we understand this amazing, invisible family of waves, what are we going to build with them next?